So hello and welcome to today's session all around enhancing data science with the Oracle Modern Data Platform. My name is Ismail Syed and I'm a data science and machine learning technical specialist at Oracle. And I'm joined with my two colleagues, Bob Peulen, who also works in the same team as a data science and machine learning technical specialist, and also Gareth Smith, who works as part of the Analytics and Lakehouse cloud design specialist team. Now, today we're going to be talking around how you can utilize some of the components of Oracle's Modern Data Platform to ensure you have a strong foundation when working through the data science lifecycle, and some of the considerations you need to look out for, along with some of the Oracle tech that can help you on that journey. Because at the end of the day, if you don't have a strong modern data platform underpinning your data science projects, the chances that they'll be successful in production will be significantly reduced. So let's get started. Now, firstly, let's get everyone up onto the same page around what is AI and ML, because these are both buzzwords which are chucked around every single day. AI this, ML that. But what actually is the difference between the two? Now, AI or artificial intelligence is any time a machine demonstrates some sort of human-like behavior. And this could be problem solving, learning something, having a natural language conversation. And the best example I like to think of is when you're shopping online or you're doing your online banking and you have a little pop-up in the bottom right-hand corner that says, "Hey, how can I help you today?" And 99.9999% of the time, there isn't going to be a physical human agent waiting for you to ask it questions in order to respond. It's going to be some sort of AI bot that's able to interpret your questions and provide you with the best response. Think of things like ChatGPT, where you can ask it questions and it responds to you. And you can essentially have that back and forth human-like conversation with it by asking questions and getting the most appropriate response back. Now, machine learning or ML is a subset of artificial intelligence focused specifically on that learning attribute. And it's the ability for a machine to learn without being explicitly programmed to do so. And it typically does this by learning on lots of historical data in order to start making future predictions. So for example, it can look at all the previous behavior of your employees that have left your company and that have remained, and using that historical data, it's able to predict into the future which employees are likely to leave next. Or by analyzing lots of historical scans of cancer tumors to be able to understand in the future which ones do look cancerous versus non-cancerous. So it's all around using that historical data to make future predictions. And finally, we have something called deep learning, which is becoming a lot more popular nowadays. And that, once again, it's a subset of machine learning, and it focuses on something called neural networks. Now, neural networks try to mimic how the human brain works. So just like we have millions, if not billions of neurons all interconnected to each other to help us with making decisions, a neural network is doing exactly the same thing, but on a computer. And it's typically used for very large and complex challenges around language, speech, images, audio, those sort of things. Now, the next question I kind of get asked is, right, I understand what AI is, I understand what ML is now, but what is data science? And a lot of people think machine learning is equal to data science and data science is equal to machine learning, which is partly true, but not completely true. If we have a look at the definition of data science just from Wikipedia, we can see data science is an interdisciplinary field that uses scientific methods, processes, algorithms, and systems to extract knowledge and insights from structured and unstructured data. And if we actually have a look at what a typical journey is of a data scientist and what they spend majority of their time doing, we can see nearly 60% of that time is around doing something with the data before you even start machine learning, whether that's ingesting the data, cleaning it, transforming it, doing exploratory analysis. These are all important tasks that need to be done before you start actually building your machine learning model. And you've all heard of the saying, rubbish in, rubbish out. And it applies here too. You need to make sure your data is in the right format and suitable before you start doing machine learning. And you can see majority of the time of a data scientist is spent dealing with that data to get it in the right format. So you should see data science more as an umbrella term, which encompasses multiple different things. whether that is the more, data engineering side of thing, data visualization, before you actually get into doing the machine learning itself. So it's important to note that data science is not just a single discipline. But, once you can kind of get all these things right within the data science lifecycle, when you build an amazing model that you can put in production, you can pretty much expect some pretty nice return on value or business benefits, whether that's, enhancing customer experience by providing a more recommended product set to them, or improved decision making by detecting anomalies and forecasting into the future, reducing costs and improving efficiency, or even just innovating with new products. But the important thing to note, to truly achieve these 4 pillars, you need to have a strong data foundation, and that data you're working with needs to be realistic, clean, and once again in the right format to be passed into a machine learning model. And there are a lot of things you need to consider, and having the right data platform is like having strong foundations to a skyscraper. It's mandatory, especially when you want to start tapping into the insights and potential of your data. Because at the end of the day, it's data that empowers AI. AI unleashes the potential of that data, and it's analytics which provides those actionable insights for you to go ahead and make those business decisions. And once you can understand these 3 concepts around data, analytics, and AI, and how you can use them in combination with each other, you can start achieving some pretty wonderful things, whether that's, identifying fraudulent or suspicious activity within transactions, or being able to predict which customers of yours are most likely to churn from a policy that's coming towards the end of it, or being able to understand your customers' buying behaviors and purchasing patterns to be able to provide them with more personalized recommendations, or even just creating a more personalized healthcare plan. These are all things you can start implementing with machine learning and AI. And there are hundreds and hundreds of different use cases, regardless of your industry or line of business you sit within. There is something you can do. But to achieve these amazing things, you do need to first overcome some hurdles and challenges. And some of these challenges have been around for a very, very long time, whether that's around, operational complexity or fragmented data, where you have your data in data silos dotted all around the organization, different data types being stored in different databases, and you can't seem to get that single pane view of all your data and query both your structured and unstructured data in one single place. Or it could be inconsistent data, which has been around probably from the beginning of time, and also vendor lock-in, where maybe you're storing and processing your data in one place, but then your insights layer is somewhere else. And there's that disconnect between the two, stopping you from gaining that insight. But Oracle's modern data platform is here to try and help overcome these challenges. So what does the Oracle modern data platform look like? So let's start with the heart of it all, where you store and process your data. And Oracle can essentially handle any workload type and any data type in one single converged database. Whether you're dealing with your standard transactional data, whether you're dealing with JSON data, spatial data, graph data, even now vector data, you can store and consolidate that all in one single place and query both your structured and unstructured data in one single query. So whatever data you have, you can bring it all into that one data platform. And once it's there, you can start then gaining the insights on top of it, whether that's using something like Apex to build an application in less than 5 minutes using low-code environments, using Oracle Analytics Cloud to be able to start building dashboards and reports and slicing and dicing your data to start gaining insights to help drive those key business decisions. We're using AI machine learning to start making those predictions into the future. And all of that, once again, is based on the data, and we can handle any data, whether that's sitting in the cloud, whether it's on premise, whether it's structured, unstructured, whether you want to bring that in real time streaming, you want to bring that in batch, we can kind of handle those workloads for you. And you can kind of see this diagram as a workflow moving from the left to the right. where if you want to achieve great business outcomes on top of your data, you need to kind of go through this journey of data ingestion, storage, processing, manipulating it, gaining insights. And once you've done that, that's where you can start really gaining that business value. So having that strong data platform is really important. And Oracle essentially live by the power of any, where we say we can handle any data from any application anywhere. And the great thing about it all, we're also open as well. We understand people aren't tied down to a single vendor or technology stack. So we want to try and meet you there in the middle, where we can say, you know what, if you are using open source technology, for example, like Spark to process your big data in memory, or you're using things like Jupyter Notebooks to build, train, and evaluate your machine learning models, we can handle those workloads and be that common denominator between all your data and technology stack by providing a combined, converged, modern data platform. So, how can the modern data platform and some of its components help with data science? So let's take a look at the typical data science lifecycle at a very high level. You can start up here at the top with data ingestion and access. You probably want to do some data exploration to understand your data transformation, cleansing, getting it in the right format. You can then build your models, evaluate them, deploy them, and then monitor them over time, because models don't always perform well forever. The important thing to note is this is not a linear process where you do step one, move on to step two. Once you finish step two, then go to step three. See, is it more of an iterative process where you probably go round this circle multiple times during a data science project? And at the heart of it all is that business challenge. Because at the end of the day, if you're not solving a business challenge, which is providing some sort of business value, is there any point in doing that data science project? That's one thing you need to keep in mind. Now, today what we're going to be focusing on more is the data side of things rather than the actual machine learning side of things. So we're going to be kind of focusing on these top three areas here around data ingestion and storage, doing data prep, exploration, cleansing, transformations, and also towards the end of the life cycle, how you can monitor your model and data over time, and how some of the Oracle components can help with that. So what we're going to do now is jump into a series of slides and demos and essentially switch between the two of them. We'll present on one of these areas, show you a demo, present on the next one, show you a demo, and we'll essentially go back and forth between them. So over to you, Gareth.
We've heard about the role that a data platform can play for a machine learning ecosystem. So let's look into the topic of that data platform in a bit more detail. Machine learning needs data, typically lots of data. The data needed can depend on the machine learning problem that you're trying to solve. In a typical business, these data could come from general business systems like ERP and supply chain systems. They could come from financial planning, treasury management systems. They could come from operational systems, from manufacturing, from logistics, from service provision. They could also come from external sources, such as partners, such as external data vendors, and they could come from detailed sources such as IT systems, log files, applications, and also instrumented infrastructure, so through channels like Internet of Things. So in short, machine learning could be employed in any type of data. Those data could come from many sources, such as core business applications, from cloud providers, SaaS applications, from line of business applications, such as from manufacturing or from logistics. They could even come from Excels, from users' desktops, and from third-party providers external to the company. So all of those data sources can provide data that need to be aggregated. All of these systems have different technical implementations, so they may have different ways of storing data, providing access to data, structuring data, describing data. They may have different data quality issues, and they may even have different ways of describing the same data. So in short, the data can come from anywhere. In addition to machine learning, there can be many stakeholders that require access to the data, such as executives, business managers who require BI dashboards and reports. You could have analytics systems. You could have data scientists digging into the data, looking for trends and insights. And you may even have data provided to people outside the organization, so through data sharing or data monetization. So the data platform can serve pretty much any user and any use case. Allowing any user to access any data can get pretty complicated pretty quickly. Even if the data are just used for machine learning, allowing data scientists and machine learning applications to access the data at bulk, in volume, over and over again, can result in a lot of complexity and a lot of problems. So some of the problems might be just simply overloading the source systems by making these requests, or managing the complexity of all of these accesses can be an overhead. It also can be difficult for data scientists to figure out which data they're looking for and how to access it. And when they are looking at data, it might be difficult for them to understand what the data represents and whether they can trust it, whether the quality is good enough, and whether the values that it represents are actually equivalent to values that might be fetched from other data sources. It can also be difficult just even to track who is using the data, what applications are accessing the data. The data platform can address these issues. The platform's data ingestion can pull data from any source in any format at any frequency and load it into the platform. The platform can store any type of data, be it structured or unstructured, at any volume from tiny to potentially massive, and retain the data for potentially very long periods of time. Data refining is a capability that can clean and transform data both as it's being ingested and later when it's on the platform to progressively refine it, to improve its quality, to extract trends and insights, metrics, KPIs and so on from the data, to produce higher quality data that can serve both machine learning use cases as well as other business use cases. And the platform should serve data to any of the interested stakeholders, including machine learning, in as easy to use and as performative fashion as possible. Finally, all of this should be subjected to governance and security, so controlling and tracking who can access the data, as well as masking sensitive data from those who are not authorized to see it. So in a bit more detail, the data ingestion part of the platform should be capable of ingesting data or fetching data from pretty much anywhere, in any format, at any frequency. The source data could reside in on-premise systems, in cloud applications, with partners. It could come from third-party data providers. It could come from file uploads and sources like Internet of Things gateways. Fetching the data may involve database queries. It may involve calling application APIs. It may involve receiving bulk transfers from source systems. It may involve end users uploading files, including unstructured data like image files, video files, and audio, and so on. It may also involve receiving streaming data from sources. So the incoming data may come from databases through SQL queries. It could come from change data capture, capturing data as it changes in real time. It could come from sources like application APIs, both on-premise and on cloud. It could come from third-party providers. The data may be streamed in. It may come in bulk uploads, batch uploads, or even micro batch uploads, possibly even file uploads from end users who upload structured data like Excels and CSV files, as well as unstructured data, things like images, audio files, video files, and so on. And the incoming data can be subject to transformations, so basic transformations like quality control and cleaning, format conversions, value conversions, and so on. Incoming data could also be used to drive real-time applications such as real-time analytics, or be fed to machine learning or artificial intelligence runtimes. The incoming data could also be used to trigger events and processes and to generate metrics and KPIs. Data processing includes the basic processing as data are ingested, but it can also include more advanced processing that happens as data resides in the platform, but as it's progressively refined and curated to produce higher quality data or derive data which might be of more use to the business. Refining the data may also include generating statistics and summarizing the data. It could include extracting trends and insights and other information from raw data. It could include processing unstructured data such as images and audio files to extract useful information, and performing tasks like sentiment analysis. In addition, the outcome of data science could also be stored for later use and analysis. So as mentioned, this data refining can happen either as the data are being ingested or later as a continuous process to refine the data that is already stored within the data platform. The data persistence capability of the data platform should be able to store any type of data. So not only structured relational data, but also document data such as JSON, XML, should be able to store spatial data, graph data, vector data, and unstructured data. The platform should also be able to elastically scale. So quite often, the platform will start small. It's needed for one or two use cases, but it should be able to grow to potentially enormous scale as it grows in usefulness and over time. And that scaling should be elastic. It should happen quickly and easily without imposing any overhead on users or without imposing any downtime on the processes that surround the data platform. So the platform itself should be very cost effective. It's going to be storing large volumes of data, and it should do so very cost effectively. It should be able to scale up and down quickly and easily with minimal user intervention. It should have very few moving parts to manage, and ideally, the skills that are required to both operate and to use the data platform should be those that are readily available on the market. The data platform should also make it very easy to access data. So it should have simple, consistent interfaces that support the various use cases such as fetching and querying. It should provide easy ways to access data regardless of what the data is. So whether it's structured data, unstructured data, whether it's graph data, spatial data, and so on. It should have consistent access controls, and it should be easily available from any application, any use case, anywhere. And those use cases that should be supported would include things like BI and reporting applications for building reports and dashboards, but also supporting data scientists who like to dig into data, explore and analyze the data. So those use cases can support traditional BI, dashboarding and reporting, but also deeper exploratory analysis and visualization. Users of the data would also include data scientists who like to dig deep into data and to explore it to extract trends and insights. And use cases built around machine learning and AI are becoming more and more common, where access to large volumes of data for training machine learning and AI models is becoming a more important requirement. Other uses of the data platform will be to provide things like data products and to export those data products for data monetization and to support application developers. All of these users and use cases should find it easy to find the data that they want, to understand the data within the data platform, and to have access controls imposed on the data that they can see and that they can access. So governance is all about knowing what sort of data you've got on your data platform. Part of the task is just cataloging the data, understanding what's there, understanding its metadata, and also capturing and detecting any changes that happen to the data or to the structure of the data over time. It's also important to build a business glossary so that business users can convert their terminology into the technical terms and the way that the data are stored within the data platform. Governance also includes things like capturing data lineage so that it's easy to track where data in the platform has come from, and to partition the overall data platform into different data domains so that allow different stakeholders to manage their part of the data. Governance and security also includes just controlling access over the data. So who can see the data, who can access the data. It includes the auditing and the logging of access to those data, and as well as the ability to mask sensitive data. So anybody who uses the data can only see data that's appropriate for them to see. And given that the data platform can store any data, security is paramount. The infrastructure should be secure, and access to the platform and to the data that it contains should be controlled. All data at rest and in transit should be encrypted, and all of this should be done through easy-to-use tooling. So to summarize so far, the data platform should be able to capture any data, store it and persist it, and deliver it for any use case. Oracle offers a complete data platform on Oracle Cloud Infrastructure. It's a comprehensive solution covering all of the capabilities and functionalities that have been described so far. It consists of a number of products or services that are easy to spin up and to use, which can be tailored in any way you like to deliver the sort of capabilities that you require from your data platform. So you can see here a number of components which deliver a lot of functionality for handling different types of data, both through data ingestion, data storage, and also data delivery or usage. These could be considered a menu of components or capabilities from which you can pick and choose the ones that you need to deliver the data platform that meets your requirements, safe in the knowledge that should those requirements change in the future, there's components and capabilities available to build out your extended data platform in whichever direction you require. So let's look in a bit more detail at some of these components. For data integration, the Oracle platform is built around a number of key services. So OCI data integration is an as-a-service, low-code tool that allows you to design and to run data ingestion pipelines without the need to deploy or to manage any infrastructure of your own. OCI Dataflow is a serverless Spark execution environment that allows you to deploy and run Spark workloads without the overhead of running and managing your own Spark infrastructure. OCI integrations excels at application-to-application integration, and in the context of a data platform, is ideal for pulling information or data from applications onto the data platform, and also for executing or orchestrating business workflows. Golden Gate is a change data capture tool that allows you to pull data, change data in real time from source databases. And streaming analytics allows you to process data on the fly as it's coming into the platform. So to perform analytics on it, or to use anomaly detection, for example, to trigger events or processes in responses to changes in incoming data. OCI streaming acts as a streaming endpoint, allowing it to receive streams of information from sources. A wide variety of compute capabilities exist, allowing you to run simple serverless functions all the way up to GPU-supported high-performance computing environments. Oracle offers several services for persisting your data. The Autonomous Data Warehouse is an Oracle database optimized for data warehouse use cases, capable of storing any type of data at any scale. The autonomous part of the Autonomous Data Warehouse name means that the service is self-driving. So many of the activities that typically a DBA would have had to perform are performed by the service itself automatically. And this type of capability can be very useful in data science or machine learning use cases, where the data scientists need to be able to install and spin up databases quickly and easily without requiring them to have extensive DBA knowledge. Object storage is a massively scalable storage suitable for storing raw data, but also suitable for storing any type of document types, even structured data, which can be mounted to Autonomous Data Warehouse's external tables. MySQL HeatWave is an alternative data warehouse solution, which offers transactional capabilities as well as high-performance in-memory analytics capabilities without the overhead or the complexity of ETL. Another data storage capability available on OCI is the Big Data Service, which is based around the Hadoop ecosystem, which is ideal for storing large volumes of data and doing processing of data in batch and on the fly. The Oracle Data Platform provides many capabilities for extracting value from your data. Oracle Analytics Cloud provides extensive analytics capabilities, allowing you to explore and to visualize your data. Oracle Data Science is an Oracle-managed environment that provides notebooks that give data scientists familiar Python and Spark-based tooling for exploring data, as well as the ability to develop data science and machine learning models. In addition to that, it has capabilities for running the models on OCI. It therefore supports the complete end-to-end data science and machine learning workflow. Oracle Machine Learning complements this by exploiting the power of the Oracle database to optimize the machine learning and the data science lifecycle by bringing the algorithm to the data, running those algorithms inside the database, close to the data, rather than suffering the overhead of extracting data to run those algorithms and compute outside the database. AI services are a collection of developer-friendly, pre-trained AI models that Oracle offers that can speed up the adoption and deployment of AI within your organization. These services cover use cases like image analysis, language processing, making predictions, and so on. And the Oracle Data Platform also includes many application development and deployment environments, allowing you to quickly and easily deploy applications that leverage your data to expose them to both your users internally within the company and also external users such as customers and partners. In addition to comprehensive support for data ingestion, data processing, persistence, and serving, the Oracle Data Platform also offers many services that help you to better govern and manage your data. These services include the data catalog, which allows you to catalog the data both within the data platform itself and also within sources outside the data platform. It also allows you and your business users to maintain a business glossary, mapping business terms that those users are familiar with the technical information that's stored within these data sources. DataSafe offers a suite of services that allow you to both assess and audit the security posture of your platform and the data within the platform, as well as offering capabilities like data masking that allows you to obscure and obfuscate sensitive data that might be exposed to third parties or unprivileged users, such as developers. The data platform runs on Oracle Cloud infrastructure, which is highly secure, from the infrastructure right up to the services and applications that run on top of it, with consistent and integrated access control and auditing across the platform. The data platform also benefits from core OCI services such as event handling and logging, allowing it to be easily integrated into wider IT control structures. This data platform is open. It can support any type of data from any data source, operate in a hybrid cloud environment or a multi-cloud environment, and it can support any end use case, such as tools running on-premise or on other clouds, as well as on the Oracle Cloud itself. Data can be ingested from any source. In addition to that, the Oracle Data Platform can federate with other data sources, acting as a single hub through which you can access data residing both on the Oracle Data Platform and elsewhere. The data platform provides easy and secure access to your data from any application running anywhere. I'll now hand over to Ismail to talk about exploratory analysis.
Perfect. Thank you, Gareth. So the next section I'm going to talk about is exploratory analysis. And exploratory analysis is a great way for you to understand the data you're working with in order to start understanding the necessary data transformation and cleansing steps you need to do on top of your data before passing it into the machine learning model to learn. And one of the best ways to do this is by visualizing the data. It's a very easy and quick way to start understanding the distribution of your data, is your dataset biased, any data quality issues, and so on. For example, being able to identify missing values in your data. So maybe you have a column that has 90% missing values. What do you do with it? Can we just drop it? Or maybe if you have only 5% missing values, do we impute it with the most frequent value or the mean value of that column? Looking at your distributions to see is your data positively skewed, is it negatively skewed? Even the balance of your data set. When you're going ahead and predicting a categorical value, is your data set biased in one direction or the other? Do you need to balance it? Looking at the data quality, are there spelling mistakes in certain values where the machine would see it is two separate values when in reality they're only one? It's just someone spelt it differently in two different occasions. Identifying outliers in your data set, so extreme values that are very high or very low for the normal behavior, and trying to understand what caused it. Was it a data entry issue, for example, when this data set was built? Or was it a very rare or extreme event that randomly occurred one day out of 1,000? And also things like feature selection, just understanding the columns that you have within your data set and identifying which columns are going to play a vital role or influence your machine learning model. So for example, someone's first name or last name has no influence whether or not they're going to buy a new TV from your store. So what you could do is drop that column and get rid of it, because you don't want to start passing redundant data that has no influence to your machine learning models. So what I'm going to quickly show you now is a little bit of Oracle Analytics Cloud, which is our enterprise analytics platform that essentially allows you to start visualizing your data, making any data prep and transformations if need be. So let's jump right into that. So before we get directly into the dashboard itself, what I thought would be quite good to do is just explain the data set that we'll be using a little bit, so you're a little bit more familiar with that. So before I go through these visuals, I'm just going to jump to the Oracle Analytics Cloud Dataset Editor, which essentially gives you a preview of your data, allows you to assess the data quality, make any necessary data cleansing and transformation steps. Now, this dataset is called the DNA dataset. Did not attend. So a data set that contains historical information about whether patients have attended or missed previous appointments. And it contains information around a person's demographics, such as age, gender, ethnicity. It contains health-related statistics, such as whether they've got anxiety, sleep disorders, alcohol abuse, their BMI, but also some behavioral patterns as well. And towards the end, you've got this did not attend column, which specifies whether or not a person has previously attended or missed an appointment. And at the top, we've got the data quality insights pane where we can start visualizing the distribution of the data, how's it skewed. If there's any missing values, it would be flagged up over here where it would say, for example, 5% might be missing or 10% might be missing. In this case, our data set is pretty clean. We can also start making transformations on our data, depending on whether or not it's a numerical column or a categorical value. So for example, with travel time, if I click on the column header, we can see some of these inbuilt calculations that you can start applying to your data. If I want to add my own calculation, let me edit the column. And you can see on the right-hand side, we have a series of different built-in transformations. So for example, I can see all the mathematical ones, and maybe I want to round my column to 2 decimal places. And I can see here it gives me a little description of how to use it. I can drag and drop this into my formula editor if I want to, or I can just start typing if I know it off by heart. So let's say I want to round my travel time to 2 decimal places. I can click on validate, and you can see over there it's gone ahead and made that change. And I can say, add step, for example. Once again, maybe let's say if we go to a categorical column, I can right click on that, and we can see a whole list of different string related manipulations, whether that's grouping, splitting, concatenating, converting to uppercase, lowercase, so on and so on. So just like you make changes before passing your data into a machine learning model, you might also want to make some changes to your data before visualizing it. So let's say we've done all the changes that we need to, we can start visualizing that data set. So here we just want to kind of get a good idea of the data we're working with, the different columns, how do they influence our target, in this case, whether or not someone attended or not. So we can see here we have just over 100,000 patients, nearly 80,000 attended, and around 30,000 previously missed appointments. We can start visualizing the distribution of our target variable, or the column we want to predict. And we can say it's got a roughly 70-30 split. So we might want to consider, do we need to balance this data set a little bit more? Are we okay as is? These are decisions you need to make before passing into a machine learning model to learn. We can then start slicing and dicing our data by different attributes. For example, travel time, and seeing how that influences whether or not people missed or attended appointments. And we can see here, for example, the people who missed appointments on average had a higher travel time, but also we can start flagging up any anomalies in our data. So for example, there's one instance of someone who attended an appointment which had a 2-hour travel time. So, maybe this is an outlier because it's a rare event, or maybe it was some data entry problems and it caused that very high value. So these are, once again, things we need to consider. We can start looking at whether or not patients show based on a history of no-shows, and we can see straight away, 64% of people who missed an appointment had previously missed an appointment in the past. If we scroll down, we can slice and dice by more attributes such as deprivation status, and we can see, people who might be living in a more deprived area have a higher rate of missing appointments compared to people who were in a slightly less deprived area. And also, finally, on the right-hand side, we can start seeing how age affects whether or not people are showing up to appointments. And here we can see there's no real trend. It's pretty much hovering around 25% across. When you get to, the slightly more senior citizens, you can see this rate drops a little bit, and they have a slightly higher show rate, and less of them are missing appointments, and so on and so on. So it's important to start visualizing your data, slicing and dicing it by different attributes to really get a good understanding of the different transformations you need to make before passing it into a machine learning model. What I'll do now is hand over to Bob, who's going to talk a little bit more around data preparation and feature engineering. So taking the output of your exploratory analysis and implementing those changes on your data set before training a machine learning model. So over to you, Bob.
So thank you, Izzy, for the data exploration part. Usually in a machine learning use case, after the exploration, let's say visually having a look at the data, you actually, of course, start changing the data. And as Izzy explained previously, in any type of use case, machine learning, AI, doesn't really matter. That's 80, 90%. A lot of work goes into data preparation, feature engineering, mostly the preparation part. Actually building a machine learning model is usually not the simple part, but it's usually not the biggest part of the entire project. There are two big steps in there. As the title says, data preparation, that is basically step number 1, and feature engineering is mostly step number 2. And data preparation is you all have heard about the phrase rubbish in, rubbish out. So if something goes in the machine learning model, you cannot expect great results from that. So the biggest thing to actually do is data preparation. There are many things you can do. On the left, you see, for example, data cleansing, and on the right, you see data transformations. If you look at data cleansing, so thinking about impute missing values. So it's not a big deal if you have some missing values in your data to use it in machine learning models. But if you have too much of missing data, or if you have skewed missing data, that can potentially be a problem when you actually train a machine learning model, and that can result in inaccurate results or biased results. Other ones are, for example, correct spelling mistakes, of course, like Izzy explained. Another one is remove outliers. And remove outliers is, for example, imagine you're building a machine learning model and you want to predict house prices. And most of your houses are, let's say, in the range of 100 to 500K. But imagine, let's say there's 1 or 2 houses that are, let's say, over $3 million of worth. Then you want to remove those because they will bias the entire model. They will be taken into account way too much, and they are not even that important. So you have to question a little bit, okay, what are we building a machine learning model for? And sometimes it is logical to keep them in there, but sometimes it's not logical, just plain business logic, to remove them. On the right hand side, you see data transformations, and there are many sorts of data transformations. And I think the most logical one, the most important one, is even business filters. And business filters are more, think about what are you actually building a machine learning model for. So imagine you're building a machine learning model for insurance policies. You have different type of insurance policies, and it could be very well that you have to build each time a different machine learning model for each, let's say, insurance policy. One for cars, one for life insurance policies, for example. They are very different from each other, and they can be different, let's say, features, columns that actually explain why machine learning model for each one of them would be important, why they would add value, why they would not add any value. So business filters very much thinking about, okay, scoping the machine learning model. There are many other examples, of course, feature selection, which features, which columns do we actually are going to use to train our machine learning model. Aggregating data, of course, on which level are we going to train the machine learning model. That can be, for example, if you think about timing on a minute level, on a monthly level, on a yearly level. But if you think about retail, that can be on a product level, let's say the individual Ben & Jerry. It can also be, let's say, more the category level, so ice cream level, for example. So there are many decisions you have to take before you actually do anything. And the last, let's say, normalizing, scaling, and coding data. That's all about, imagine you have the house prices again, normalizing, scaling, and data. Imagine you have 2 columns. One, let's say, ranges from 0 to 5, and a different column ranges from, let's say, 0 to 100. And they have different ranges. And even that, not having the same range, that can affect the machine learning model. So normalizing and scaling means that you basically make them, let's say, similar, and that the machine learning model sees them as similar in importance. Because 0 to 100 would already ensure that if, let's say, the value is set at 99, it would already have more importance than the other column. And you don't want that, and might not be true. And encoding data, for example, means if you have a lot of categories, like string variables, really like type of plants, for example, we need to convert that basically to numerical representation. That can be different type of encoding data. If we look at, for example, feature engineering, and feature engineering is mostly about, let's say, okay, we did data preparation, we had certain columns, we fixed them, we make sure they are all aligned, they're all scaled in the same thing, etc., etc. There are no missing values anymore, or we filled them in the correct way. And feature engineering is all about, okay, how we can add more features, how we can add more features or change features, combine features, extract features, let's say from external data or from the current feature set, and make the machine learning model more, let's say, more predictive. And on the left, there's a couple of examples. If you think about customer churn prediction model, think about adding the recency of last purchase. So probably the more closer somebody actually made a last purchase, probably less likely they will not actually churn, let's say, in the next week or so. There are more examples of that. And the fraud anomaly detection, for example, you see the last one, morning, afternoon, weekend, weekday. You can imagine that fraud doesn't usually happen on a Monday morning. It probably happens more on the weekends, just my assumption. But there are logic to it, right? And these logics you can add, or these features you can add to it, they are probably not in the actual data set. So you can, based on, for example, the timestamp that a transaction happened in the fraud use case, you can derive whether that was a weekend, you can derive that was what type of day, for example, the time of hour, done by who, things like that. So we can add things to the XST model. And I think that's one of the big, also fun parts of building a machine learning model. That's not just having features, changing them, and off you go, you train a machine learning model. Now there's a lot of business logic to it, adding things, adding your own logic to it, and actually building that for the machine learning model. So let's do a small example of data preparation and feature engineering. Let's swap to my browser. Let's go here. So we're in an OC Data Science notebook, and OC Data Science notebook where you can collaborate data scientists in there. We'll explain that afterwards a little bit. But what we did here, I'm not going to explain the Python code one-on-one. What we did is basically show you very quickly an example of, imagine we build a machine learning model, and we do that twice. First, we do the machine learning model without not much preparation, not much changes, and then we use an AutoML functionality that does a lot of changes. That helps us to do, let's say, data preparation, feature engineering, scaling the models. All of that is, let's say, handled by it, and see what the result is. And we don't actually change the data set. So let's do an example. So we start with importing libraries, not important right now, but we are now loading on the left, we are loading, let's say, the did not attend data set. That's a similar data set as Izzy showed you before, and now in the table. So this is we load the CSV file, and then we can see the IDs for each and every, let's say, customer. And if we go on the very right hand side, you see did not attend. And that's something we want to predict based on all these variables that are already in there. I have BMI, we have travel time, anxiety. We have a lot of data to actually see, okay, can we predict whether people did not attend the meeting? If you have have a close look a little bit, we can see the 1 means that people did not attend their appointment, and 0 means they did attend the appointment. So you can easily see that at least 27% of the people that had an appointment did not actually attend. And that's quite, I think, quite a high number in terms of non-attendance. We'll skip that for now. We'll stay at that for the data preparation. But let's try and build a machine learning model. Let's do that twice. We start with using just some open source machine learning model, and afterwards we do the exact same thing, but then we use we change the features more, etc. So this script here basically says, okay, let's take all these features on the left, and we try to predict did not attend, yes or no, did not attend. That's basically what happens here, and we don't change very much. The only thing that we do is scaling. And scaling means, right, imagine have the different scaling or the different features. For example, you can use age, for example, together with a different numerical range. We do that, but the rest we don't really change anything closely. So let's run this, and basically we change the data, we test it, and we split it in train and test sets and all that, and we get an accuracy of the machine learning model of 0.72. And so the accuracy without much changes, is 0.72. So let's build a machine learning model again, but now we are using the AutoML functionality from Oracle, Oracle ADS. That's a Python package. It's open source available. And basically what it does multiple things. We load the exact same data set, but it helps us do, let's say, pre-processing. So it will help to clean the data. It will help looking at the missing values. It can normalize features. It can identify multiple algorithms. And the first one, we just selected one algorithm, but now it will look at multiple algorithms to see, okay, which one performs the best. It will also do adaptive sampling. And that means if you have a highly unbalanced data set, let's say 99 versus 1%, then it will balance that, or it tries to balance that a little bit, so that if you build a machine learning model, let's say only just predicting that 1%, it will be more correct. Because if you have your highly unbalanced data set and you do, for example, classification, then you will be mostly correct. It will be correct. Your accuracy will probably be in 99%, but that is not really accurate, because the data set was very unbalanced to start with. So that's not really great. It will help us to do that. It will help us with feature selection. So basically selecting features that are important and dropping features that it finds not important or have zero correlation with the model. And the least sexy, but most important, it will do some tuning. And tuning basically means, actually, you see many different models here, but each model can be tuned a little bit so that it performs better. So if you think about a decision tree, decision tree is literally that. It's a tree. Imagine a tree, but a tree can be very big. It can be very wide. It can have many leaves. It can have many trees or many branches, for example. So the tree can change over time. And basically what it does, right, it will change the tree. It will look at different settings of the tree and see what works best. And in the previous model, we didn't really have that, and we have to tweak it ourselves. So let's do that. That's basically this script, and we use the exact same data set that did not attend, and we try to do that. This takes a bit longer, but if you look clearly, this is the process of running. And we see, for example, here you see running auto processing, right? So it looks at the missing values. It is doing some data preparation steps. You can see it's looking at different models. So it's selected a specific model. This is an extreme grading booster classifier. It seemed that appropriate for this type of model what we did. You can see even at feature selection, it's now tuning this specific model, and now it's more or less done. And so AutoML completed. So it did a lot of steps for us without us actually thinking about it. And we can make that a summary. So if you look at, okay, what actually did you do? Let's scroll down a little bit. I did a lot of things. You see a table with algorithm, usually a lot of these type of algorithms, and even way more, going down and down and down. And they are ranked on the validation score. And for now, that's our accuracy. So if you compare the previous accuracy, which was 0.72, with this one, which is 0.74.90, which is maybe not that significant higher, but still, we didn't actually change anything, and we just ran it across the AutoML functionality, and we're changing the features. We actually increased the accuracy without actually changing a lot of things. So the AutoML functionality did a lot of data preparation and feature engineering for us. That's just a small demo. And of course, if you do this way more significantly better, adding more features, the accuracy can go up and up and up and up, of course. And that's, of course, the fun of machine learning models. Thank you for that. I will now hand over to Ismail to talk about data model and data model monitoring.
Perfect. Thank you, Bob. So once you've built, trained, and you've got your model deployed in production, a lot of people think you can just dust off your hands, give yourself a pat on the back, and job good, well done. However, this is not the case. Once the model is in production, there's a few things you still need to keep an eye on. And one of that is data and model monitoring. At the end of the day, once your model's in production, it's not going to perform optimally forever. For example, when you initially train and tested your model, it could be achieving, 95% accuracy. A few months down the line, it could then drop down to 92% accuracy. And then a few months after that, it could drop down to maybe 89% accuracy. And at that point, it's kind of crossed your threshold and it's no longer fit for purpose. We can kind of break down this into two areas around data drift and model drift. So data drift, as the name suggests, your data drifts over time. So the data you trained your model on originally might not be the same data that's being passed into your model a few months down the line. And what I mean by that is maybe the data set statistics are slowly changing over time. So maybe the maximum value has now increased. The minimum value is now decreasing. The standard deviation, the mean, the average are slowly changing over time. And that could be because of a change in the environment or evolving behaviors, data quality issues, which is making the data set over time look slightly different to what it was originally trained on. And as you can imagine, if your model is now seeing this new distribution of data, which it's not familiar with, it's not going to perform as well. And the second half of this is model drift, is where your accuracy, or I should say your performance of your model, slowly degrades over time as well. And one of the main factors to that is data drift, because it's getting different data, it's not used to it, the model will perform not as well, but also things like concept drift. So if we take as an example fraud detection, and what actually constitutes to fraud might change over time. Maybe people have found a new way to commit fraud and the model was not trained on that data. So they can start hitting this new technique, committing more and more fraud, and your model can't pick it up. So it's kind of going under the radar. And that's because, once again, your data set that you originally used might not be able to incorporate the data needed to pick up that new type of behavior that they're showing. So it's very important to keep track of your model over time, see how it's performing, but also your data to see, is it the data that's changing that's influencing your model's performance? So let's take a quick look at a demo where we'll show you a library within OCI Data Science called ML Insights, which allows you to track both your data and your model drift over time. And we can see how we can visualize that data in Oracle Analytics Cloud later on. So let's jump right into it. So let's bring up OCI Data Science Service. So you saw Bob using this earlier to kind of build and train his machine learning models, the open source one versus using the AutoML capabilities. And within this notebook, what we're going to quickly have a look at is some of the different drift metrics and statistical calculations you can start doing on top of your data to track both your data over time, but also your model performance. So at a very high level, first we'll look at model performance, and you can start tracking different performance metrics, whether you're using a classification model or a regression model. We've got things such as accuracy, precision, recall, false positive, false negative, ROC, AUC, those sort of things. And for regression models, you've got the mean absolute error, squared error, R-scored, so on and so on. So all the typical performance metrics that you're used to when it comes to evaluating your models, you can use this to track how your model is changing over time. We've got conflict metrics to see if there's differences in predictions over time, and also some drift metrics on top of your data. So being able to see how your numerical features are drifting over time, but also your categorical features as well. And we have some of those common industry standard drift metrics, such as callback LIBOR, population stability index, chi-squared, and so on. And also, what's also important to monitor over time is your data quality and integrity to see how, for example, the minimum value or the maximum, the mean, the standard deviation is changing over time. Are you having more duplicated data? Is the count of data changing? Seeing how your data is changing over time as well. So this is another thing that's important to measure as well. And essentially within OCI Data Science, you can import the Machine Learning Insights library, which has all these calculations built in for you, and you can essentially start implementing them on top of your data. So you can take a snapshot of where you trained your data, and then you can go ahead and run these statistics and calculations on top of your data at set intervals. So maybe on a weekly basis or a monthly basis, you can pass in that new batch of data to these calculations, and we can compare it to that baseline data set to see how it's changing week in, week out, or month in, month out. So I'm not going to go through the code. No one wants to see code, but essentially this library will automatically kind of do all those calculations for you. But the great thing is you can start visualizing that output within Oracle Analytics Cloud. So we took a look at Oracle Analytics Cloud, or OAC, earlier on in the session, and essentially it just gives you a nice way to visualize your data. And in this case, we're going to start visualizing the output of our machine learning monitoring. So let's say we trained a model on the 3rd of July, and then every week we made a batch set of predictions, and we ran those batch predictions through our calculations to calculate both the drift metrics for data and the model monitoring, and we can see how that's changing over time. So we can see here our baseline model accuracy started at 78, currently it's at 74. You know, maybe the threshold was at 75% and it's kind of gone below it. Hence, we can make it red using conditional formatting. We can look at other performance metrics such as precision, recall, and how that's changed from when we originally trained our data set to our current batch predictions. And we can, you know, see how it's changing over time. We can look at individual columns such as the patient's travel mean time. And we can see here's our baseline data set. And every week we have our reference data set, which we can compare. And we can see once again, you know, over time, you see the mean travel time is slowly decreasing. Same with age, we can look at the min, max, standard deviation. Down below in the bottom left, we can look at our drift metrics. So here are some drift metrics for the person's BMI value. Is it changing over time? And you can compare it against those different drift calculations we have, whether it's callback LIBOR, Jensen-Sandman, population stability index, and so on. And once again, we can see how that's changing over time through a chart through a table, but also a visualization as well. And finally, in the bottom right, for BMI category, which is a categorical column, we can use chi-squared to calculate that drift and how that's changing week in, week out. So you can see how easy it is to start visualizing the output of your calculations for both your data and your model monitoring, and being able to flag up when things are crossing a threshold to say, right, at this point, we need to now retrain our data. So let me quickly jump back to slides to finish off. So we've come to the end of our session, so I hope you've all learned something new today. We started off looking at what AI, machine learning, data science is. We touched on the Oracle Modern Data Platform and why it's important to have that underpinning your data science solutions. And we took a look at a series of demos of how certain components of the Oracle Modern Data Platform can help with that data science lifecycle. Now, just as a reminder, cloud coaching events are happening every Wednesday at 11 o'clock in the morning, Central European time. So please check that out. There's some links there at the top. But apart from that, hope you enjoyed. Thank you.